Okay, so welcome to the course on analog and digital electronics. See, up till now, in case of analog and digital electronics, we have gone through the internal structure and the electronics of the operational amplifier. Okay, so we have mentioned that the operational amplifier is generally used in the closed loop configuration using feedback. Okay, and we can form countless simple circuits using one or more operational amplifier along with some external resistors and the capacitors, right? And talking about the applications of operational amplifier, we can classify as linear and non-linear type of application. Okay, so basically what happens in linear applications? See, in the linear applications, output voltage varies linearly with respect to input voltage. Okay, so in such linear applications, a negative feedback is used from the amplifier output to the inverting input terminal. Okay, and in case of non-linear applications, a feedback is provided from the output to the non-inverting input terminal. Okay, so suppose we are providing some feedback over here. Okay, I am providing with the dotted line. Okay, this is the feedback which we are providing to this inverting terminal. Okay, in that case we may have negative feedback. We may have negative feedback, but what will happen in this case, my output is going to vary linearly with respect to the input, and that is why we may have some linear applications. Okay, but suppose I am providing the feedback to this non-inverting terminal. Okay, in that case you may say we have positive feedback. Okay, this indicates the positive feedback. But what happens in this case? The output will not behave in linear fashion with respect to input. Okay, so that is why the application is called non-linear applications. Okay, so using this feedback, we may have linear applications of op amp as well as non-linear applications of the op amp, and it is very easy for you to identify whether the op amp is giving us the linear relationship between the input or non-linear relationship. How? Just see at what terminal we are providing feedback. If it is provided to inverting terminal, then we are having linear applications, and such linear applications includes voltage follower circuit, then adder, subtractor circuit, okay, etc. Right? Instrumentation amplifier is also there. Integrators are also there. Okay, integrators, differentiators. Okay, so these are the some of the linear applications of operational amplifier. On the counterpart, suppose we talk about the non-linear applications, right? So here we are providing the feedback to the non-inverting input terminal, and that feedback may be provided to using some non-linear elements like diode, transistor, etc. Okay, and these non-linear circuits have highly non-linear input to output characteristics. Okay, so talking about the typical non-linear applications, they are precision amplifier, rectifier, precision rectifier. Then you may call log amplifiers, anti-log amplifiers. Okay, we are going to see each and every applications in detail. Then comparator, and Schmidt trigger circuit. Okay, so these are the some of the applications, non-linear applications using operational amplifier. Okay, so in this typical module 2, we are going to see the linear applications of op-amp, and in the next module we will understand about the non-linear applications of the op-amp. See, whether you are dealing with non-linear applications or linear applications, remember always the concept of virtual ground plays an important role in studying various application circuits. Okay, so what we have seen in case of virtual ground, see, if one terminal is at the ground, then the potential of the another terminal should also be at the ground. Okay, so we can say these two terminals, inverting terminal and non-inverting terminal, are virtually short. They are not physically short, but you can consider they are virtually short. So whatever potential will be available at one terminal, same potential will be appear at the another terminal. Okay, remember this for analysis purpose of the amplification circuits. Right. So we will start with the linear applications. The first linear applications which we are going to discuss is the voltage follower circuit. Okay. Now, as the name suggests, voltage follower, we can assume that it will follow the input voltage. Okay, so if you find a circuit in which the output voltage follows the input voltage, it is called voltage follower circuit. Okay, and looking back at the circuit diagram of voltage follower, then here we have one operational amplifier, right? Now we will have inverting and non-inverting terminal as it is, right? And we are measuring our output voltage V0 over here. Now in voltage follower circuit, what we are doing, see, we are providing feedback, okay, without any resistor. Okay, so feedback resistor is not available, and to the non-inverting terminal I will be providing one input signal like this. Okay, so this is my input signal voltage V in. Let us call this as terminal A, this being terminal B. Okay. So this typical circuit shows a voltage follower. Okay. Now let us try to understand how this circuit is called a voltage follower circuit. Okay. So if you look at this node B, okay, you can see the node B is directly connected to this source of magnitude V in. Okay, so what we call this node can be called as super node because it is directly connected to the source of voltage. Okay, so this node B will be at potential V in. Okay, now what should be the potential at node A according to virtual ground concept? Node A will be the same will be at the same potential as that of node B, right? So if we talk about VA and VB, then VA and VB in this case will be equal to V in. Okay, so we have this, right? VA equal to VB equal to input voltage V in, right? And if you see, we are available here with VA voltage, and this VA voltage, this node A is directly connected to output terminal V0, right? So if we talk about the output voltage V0, then it is also equal to VA. Okay. So V0 is equal to VA. That is what we know. Let us call this as equation number 2. So now if you equate these two equations, equation number 1 and equation number 2, then what you can say? Equating equation 1 and 2, we will be able to say that output voltage V0 is equal to input voltage V in. Okay. So whatever may be the input signal, we will have the same output voltage signal. Okay. And talking about the gain provided by this circuit, what should be the gain? Okay, it should be equal to 1. So gain is equal to unity in our case. Why? Because output voltage, magnitude of input voltage and output voltages are same. Okay. So you can say that the output voltage V0 is equal to input voltage V in. If we increase V in, then V0 also increases. If we decrease V in, then V0 also decreases. Okay. So ultimately, as in conclusion, what we can say is the output will follow the input. Hence, the circuit is called voltage follower circuit. Okay, and sometimes it is also called as source follower. It is also known as source follower circuit, or it is also known as unity gain amplifier, because this circuit provides gain is equal to 1. Unity gain amplifier. We can also call it buffer amplifier, or isolation amplifier. Okay. So talking about the waveforms, input and output waveforms, it can be well predicted by you, because as we know, the output voltage waveform will obviously follow the input voltage waveform. So suppose this is my input voltage signal, okay, V in. And if we talk about the output voltage signal, then output voltage will follow the input voltage like this. So this is the typical input and output voltage waveform in case of voltage follower circuit. Okay, you can see very simple circuit is there. Just we are providing feedback without connecting any feedback resistor. Hence, whatever gain provided by this circuit, that will be equal to 1. And this is the reason why this voltage follower circuit is also known as unity gain amplifier. Okay, so magnitude and phase of output voltage will be equal to input voltage. Okay. Now one may say, if output voltage is same as the input voltage, then what is the need of providing this additional circuitry? Okay, the question should arise in your mind. Suppose we are getting the same voltage over here, that voltage we are providing over here, then why we include this much of circuit? Okay, either we can directly give this voltage to the circuit directly, whatever load is connected over here. Okay, we are not doing this because of certain advantages that are being offered by this particular circuit. Okay, and these advantages are, the first and foremost advantage is it will offer you very large input resistance. Okay, and we know when very large input resistance is offered, that means we can almost neglect the effect of loading. Okay, so typical value are in mega ohms. Okay, this is the first. Second, it will offer you low output impedance or resistance. Okay, this is also advantages, as we have discussed so many times, right? And then if we talk about the operating range, then this will provide a large bandwidth. Okay, and fourth example advantage is output follows the input exactly without any phase shift. Output follows the input exactly without any phase shift. Okay, so these are the various advantages offered by this typical circuit. Okay, now because the input resistance of the voltage follower is extremely large, it will draw negligible current from the signal source. Therefore, we can say signal source is not loaded. Okay, and this property is most suitable in case of instrumentation amplifier, which is generally used to amplify the signal output from a transducer. Okay, if the output of a transducer is directly applied to the input of an amplifier which does not have high input impedance, then there is every possibility that the transducer may get loaded. Okay, and this loading will alter the characteristics of the transducer. And to prevent this, the voltage follower circuit can be used in between the transducer and the amplifier. Okay. So such an use of the voltage follower is called isolator or a buffer. Okay, and hence the name is given to you, buffer amplifier or isolation amplifier. Okay, so this is the typical voltage follower circuit. Now let us talk about the practical use. Okay, where you can use this voltage follower circuit. Okay, see, I am taking one typical circuit where I am directly connecting my source voltage to the load. Okay, so suppose we have a supply voltage of Vs. Okay, there is some source resistance, and this voltage is being given to the load resistance. Okay, here is my load resistance RL. Let us say the value of load resistance is 2 kilo ohm. Okay, and it is producing some output voltage V0 across the load. This is my source resistance. The value of typical source resistance is 200 kilo ohm. And whenever we switch on the supply, the current will flow in this typical direction. Okay, so this is the source Vs which is driving the load. Okay, so this is the circuit which we need to consider. Okay, it is a circuit of a voltage source which is driving this load of 2 kilo ohm. Okay, now you can see here the source resistance is 200 kilo ohm and load resistance is 2 kilo ohm. Okay, so the source with this Rs represents an equivalent circuit of many practical situations, like you can say transducer which is driving a load. Okay, if we consider the potential divider, then what is the output voltage? See, output voltage V0 in this case will be equal to RL divided by Rs plus RL into supply voltage V0. Okay, so RL value we know, RL is 2 kilo ohm, Rs is 200 kilo Vs. What is it? It is 0.01 times Vs is available to drive the load. Okay, so we can say there is a severe attenuation, and this is nothing but it is called loading effect. This is called loading effect. Now let us try to use voltage follower circuit to connect this source to the load. Okay, so what I will do, I will separate this source with this load, and in between we will try to connect one voltage follower circuit, and let us see what happens when we are using this voltage follower circuit. So let us say we have this voltage follower circuit. This is my inverting terminal, non-inverting terminal, and here I am providing output. Okay, so load resistor we will connect over here. This is the load resistance. Output voltage we are measuring over here. Value I am not changing, it is 2 kilo ohm only. Okay, and we will provide a feedback to inverting terminal like this. Okay, now at the input side we will connect our source supply voltage. Okay, so this is the supply voltage Vs having Rs in series. Typical value of Rs is provided 200 kilo ohm. Okay, so this dashed orange box indicates the voltage follower circuit. Okay, you can compare this circuit with the previous one over here. Okay, just in between this box I am providing the voltage follower circuit. That's it. Okay, now let us understand. Okay, what will happen? See, here we have the loading effect, right? So this circuit should reduce, should reducing the loading effect. Then and then we can say the voltage follower circuit is useful. Okay, so we have used voltage follower to connect the source to the load as this figure. Okay, now here you can see this voltage follower circuit is providing very large input impedance, so no current can go into the op amp, and the voltage at non-inverting terminal is Vs. Okay, and due to the voltage follower, what is happening to the output side? Output side voltage V0 will be equal to Vs. Okay, this is what voltage follower circuit is known for. So the loading effect, you can say, almost gets eliminated due to the use of this voltage follower circuit, as it has very high input impedance. Now compare this equation. Okay, let us call this as equation B, and this is my equation A. Okay, without the use of voltage follower circuit, my output was only 0.01 times the input voltage, while in this case the output voltage is equal to input voltage. Okay, so effect, loading effect is almost neglected with the help of this voltage follower circuit. Okay, so this is the typical practical use of a voltage follower, right? So you can use this voltage follower circuit whenever we need to minimize the effect of loading, right? Now let us go through one more application, linear application of operational amplifier, which you will find frequently, and this circuit is known as summer or adder circuit. Okay, so we know that the input impedance of an op amp is extremely high. Okay, so more than one input signal can be applied to the inverting amplifier, and such circuit will give the addition of the applied signals at the output, and this is the reason why it is called summer circuit or adder circuit. Okay, so depending on the signal sign of the output voltage, the summer circuits can be classified as inverting summer or non-inverting summer. Okay, so we may get inverting summer when we have the output voltage 180-degree out of phase with the input voltage. Okay, so in that case this adder circuit or summer circuit can be classified as inverting summer, and suppose the output voltage is in phase with the input voltage, then we may have non-inverting summer. Okay, so understand what we are doing. See, we are providing number of inputs, okay, number of voltage sources at the input side, and at the output we will get the addition of these voltage sources. Suppose 1 volt has been applied, then at the another input 2 volt. Okay, so output should be 3 volt. Okay, so output may indicate -3 volt or +3 volt, depending on which side we are providing the input signal. If we are providing the input voltage to the inverting terminal, then we will get -3 volt. Otherwise, we will get +3 volt. So let us try to understand this with the help of circuit diagram. Okay, first we will talk about the inverting summer. Okay, so we have an operational amplifier whose non-inverting terminal is grounded. Okay, and to the inverting terminal, now as we have discussed, we will provide multiple number of inputs. Say this is my input V1 and this is another source, say V2. Okay. This being resistance R1, this being resistance R2, and we have feedback resistance RF. Okay. And we are measuring output voltage V0 over here. Okay. This is V1 and V2 which we need to apply. Okay. This is terminal A and this one is terminal B. Okay. And this supply source is V1 will cause some current I1 to flow in this direction and V2 will cause some current I2 to flow in this particular direction, and then this current will flow through feedback resistance RF to output voltage V0. Okay. So this circuit shows inverting summer circuits. Okay. In this circuit, all the input signals to be added are applied to inverting input terminal of the operational amplifier. Okay, so we have seen two input signals, as you can see, V1 and V2. Now here, if we talk about this point B, okay, point B you can see is grounded. Okay, and due to virtual ground concept, what is the potential at node A? Node A is also at ground potential. Okay, so we can say VA is equal to 0 because VB equal to 0. How? Virtual ground concept. Okay, so we will call this as equation number 1. VA is equal to 0. Now consider the input side. Okay, I am talking about the current I1. Okay, suppose I want to find out the magnitude of I1, then I1 is equal to V1 minus VA divided by R1. Okay, but VA is equal to 0, so I1 will be equal to V1 divided by R1. Similarly, we can find out the current I2, which is equal to V2 minus VA divided by R2. Again, in this case, VA equal to 0. So I2 will be equal to V2 divided by R2. Okay, now these two currents are meeting at this junction A. Okay, and there is one outgoing current which is flowing through RF. Now there are two possibilities. This current can go in this particular direction or current can go into the operational amplifier, but this is not possible as this operational amplifier will provide very high, very large input impedance. Okay, so the current flowing toward the input terminals will be equal to almost 0. Practically there is some voltage, but it is negligible. So entire amount of current will flow through this feedback resistor. Okay, so if we apply Kirchhoff's current law at this node A, then we can say that current I is equal to I1 plus I2. Okay, so let us apply KCL at node A. Okay, so applying KCL at node A, and considering input op-amp current is 0, and as input op-amp current is 0, we will get I is equal to I1 plus I2. Okay, let us call this equation number 4. Okay, now this same current is flowing through this feedback resistance RF also. Okay, so let us try to find out the magnitude of RF in output side. Okay, so from the output side, what is I? See, current I is flowing from terminal A to output terminal. Okay, so VA to V0. Okay, that is the difference VA minus V0 divided by RF. Okay, but VA, as we know, is equal to 0. So our output side, the magnitude of current will be V0 divided by RF. Let us call this as equation number 5. Okay, so we have these equations of I. Okay, and we have the equations of I1 and I2 also. Okay, so if we substitute this 5, 2 and 3 in equation number 4, okay, values of I, value of I1 and value of I2 from equation number 2, equation number 3 and equation number 5, what we will get is, what is I is equal to, okay, first I'll write down substituting 5, 2 and 3 in equation number 4. Okay, so we will get minus V0 by RF is equal to V1 by R1 plus V2 by R2. Okay. So what we are interested in? We are interested in finding out the output voltage V0. Okay, so output voltage V0 is equal to minus, I will take RF on the left hand side, right hand side of the equation. So minus RF by R1 into V1 plus RF by R2 into V2. Okay, so this is our equation of output voltage. Okay, suppose all the resistances R1, R2 and RF are equal. Okay, so if R1 is equal to R2 is equal to RF, in that case V0 will be equal to minus V1 plus V2. Okay, so what we can say from this equation? We can say that the input signal sources are added. Okay, but the output voltage will be 180-degree out of phase with the input voltage. Okay, so by properly selecting the values of RF, R1 and R2, we can have some weighted addition of the input signals. Okay, like we can say the input signal may be V0 will be equal to A times V1 plus B times V2. Okay, this is possible by selecting the proper values of R1, R2 and R3. Okay, and we can add n number of input voltages using this typical circuit. Okay, so the magnitude of the output voltage is sum of the input voltages, and hence the circuit is called summer or adder circuit. Okay, so here we are getting output voltage 180-degree out of phase with the input voltage. Now let us talk about the non-inverting summing amplifier. Okay, so we will go through the circuit of non-inverting summing amplifier. So we have this source. Now supply voltage is not to be given to inverting terminal. Okay, so I am grounding this inverting terminal, okay, like this. We have to provide negative feedback, and that is why we will provide the feedback to non-inverting terminal only. Okay, so this is my feedback resistance RF, and this is resistance R1. Now I am providing the supply voltage to the non-inverting terminal. Okay, so again we will give two input signals, V1 and V2. Okay, through this resistance is R1 and R2. Okay, let us say this is node B and this is node A, and we are measuring output voltage V0 over here. Okay. Now let us talk about the currents. See, the current I1 will flow through resistance R1 and current I2 will flow through resistance R2. Okay, and finally the current I will flow in this typical direction. Okay, like this. Okay, so this circuit shows non-inverting summing amplifier. Okay, now here talking about the node or voltage at node B. Okay, let us say the potential at node B is VB. Okay, now what will happen to node A? Node A will be at the same potential as that of B because of the virtual ground concept. So we can say VA is equal to VB in this typical case, right? Now talking about the input circuit, what is the magnitude of I1? I1 is equal to V1 minus VB divided by R1. Okay, and what is I2? I2 is equal to V2 minus VB divided by R2. Okay, and this current I1 and I2, as you can see, are going into the input non-inverting terminal of the operational amplifier, but we know that the input current of op amp is 0. Okay, but as the input current of op amp is 0, what we can say that I1 plus I2 is equal to 0. Okay, I1 plus I2 is equal to 0. Let us call this is my equation number 2 and this is our equation number 3. Okay, now you know the values of I1 and I2. Okay, just put these values of I1 and I2 from equation number 2. So we have V1 minus VB divided by R1 plus V2 minus VB divided by R2, and that is equal to 0. Okay. Now let me write down, let me divide this term. Say V1 by R1 minus VB by R1 plus V2 by R2 minus VB by R2 equal to 0. Okay, let us take this VB on the right hand side of the equation. So we have V1 by R1 plus V2 by R2 is equal to VB is the common term in both divided by into 1 over R1 plus 1 over R2. Okay, so from this we will be able to calculate the value of potential at node B, VB, and it is equal to R2V1 plus R1V2 divided by R1 plus R2. Okay, this will be our equation number 4. Okay. So now we know that the potential at node B is equal to VB. Okay. Now considering node A, okay, you can see the current I is flowing from output voltage V0 terminal to A terminal. Okay, so if we talk about I, then IA is equal to VA divided by R, or you can say VA is equal to VB. So VB divided by R. Okay, so at node A, we have I is equal to VA by R, or we can say VB by R. Why? Because VB is equal to VA according to virtual ground concept, right? Now, this current I is flowing from feedback resistors RF also. Okay. So, I is equal to V0 minus VA divided by RF. Okay. And I is equal to V0 minus VA divided by RF. Okay, what is VA? VA is equal to VB. So V0 minus VB divided by RF will be here. Okay, so these two are same. Okay, let us call this as equation number 5 and equation number 6. We can equate these two equations. So we can write down VB by R is equal to V0 minus VB divided by RF. Okay, now simplify the term. V0 by RF is equal to VB into 1 by R plus 1 by RF. Okay. So we can write down the output voltage equation V0 as VB into R plus RF divided by R. Okay. We will call this as equation number 7. Okay. Now we have one equation of VB. Okay, we have derived the value of VB according to equation number 4. So let us put this value of VB in this equation. Okay. So we will have V0 is equal to R2V1 plus R1V2 into R1 plus R2 multiplied by R plus RF by R. Okay, just simplify the term. We will get R2 into R plus RF divided by R into R1 plus R2 times V1 plus R1 into R plus RF divided by R into R1 plus R2 times V2. Okay, so this is the equation of our interest. This equation shows the output voltage. It is nothing but the weighted sum of the input. If all the values of these resistances are same, then what is output equation? Output equation is V1 plus V2. Simple. Okay, so if R1 is equal to R2 is equal to R is equal to RF, then V0 will be equal to V1 plus V2. Simply, you can see two input signals are added together. Okay, so there is no phase difference between the input and output, and this is the reason why it is called non-inverting summer amplifier. Okay, so this is another applications of operational amplifier where we want to add two or more voltage signals. Now to these circuits also we will be able to add number of input signals and number of input signals V1 plus V2 plus V3 plus V4 up to Vn. Okay. Now apart from this summing amplifier, we may also get the average of the input signals at the output. Okay, and that circuit is known as average circuit. So let us have a look at this average circuit. Okay. Now we don't require any additional circuit. Suppose we are dealing with the inverting summer circuit. Okay, and in the inverting summer circuit only, if we have the values of resistances as R1 equal to R2 and that is equal to R. Okay, and value of feedback resistance is half of that, that is R by 2. Okay, so if our selection of the resistance is as this, all the resistances R1 and R2 is equal to R and feedback resistance is half of that value. Okay, in that case, see, if we already have derived the equation of output voltage. Okay, let me write down the equation one more time. Okay, V0 is equal to minus Rf by R1 times V1 plus Rf by R2 times V2. Okay, this is the equation which we have derived. Okay, let us go back to this equation here. I am talking about equation number 6. Okay, now in this case we are considering R1 is equal to R2 and Rf is equal to R by 2. Okay. So let us put these values. We will have Rf is equal to R by 2 divided by R V1. Rf is equal to R by 2. R2 is equal to R times V2. Okay. See what we are getting. R will get cancelled out and we may have minus of V1 by 2 plus V2 by 2, which is nothing but average of these two voltages. Okay, so output voltage V0 is equal to minus of V1 plus V2 by 2. Okay, so the output which we are getting is nothing but the average of the two input voltages. So you can say the circuit acts like an averager. Okay, so if we have n inputs, then output will be equal to V1 plus V2 up to Vn by n. Okay, in that case our values of resistances will be R1 equal to R2 equal to R3 equal to Rn equal to R, and what is feedback resistance? Feedback resistance should be equal to R by n. Okay, so if we select these values of resistances, then we will have an average circuit. Okay, this is called averager, right? So this is typical applications of operational amplifier. Right, now let us try to understand this with the help of some example. Okay, we will try to solve some basic examples. See, I have been given one circuit. Okay, non-inverting terminal is grounded and to the inverting terminal total 3 different voltage sources are connected. Okay, first one is plus 2 volt, plus 1 volt, plus 4 volt. Resistances are 1 kilo ohm each, and feedback resistance is also having a value of 1 kilo ohm. Okay, and I am getting some output voltage V0 over here. Okay, what you need to do is try to find out the output voltage V0. Okay, so here we have the value of R1 equal to R2 equal to R3 and that is equal to 1 kilo ohm, and feedback resistance Rf is also having a value of 1 kilo ohm. Okay, now for this typical circuit if we wish to write down the equation for output voltage, then it is equal to minus Rf by R1 times V1 plus Rf by R2 times V2 plus Rf by R3 times V3. Okay. Now values of Rf and R1 are same, 1 kilo ohm each. Okay, so these ratios will get vanished. So now we will be available with this equation, minus of V1 plus V2 plus V3. Okay, so magnitude of V1 is known to you, 2, V2 is 1 and V3 is 4. That is equal to minus 7 volt. This is the amount of output voltage which we will get. Okay, see, quite easy. Now suppose the supply voltage is provided to non-inverting amplifier. In that case, we need to find out the node voltage VB according to this equation. Okay, we already have derived the equation for VB. It is R2V1 plus R1V2 divided by R1 plus R2. Suppose values of R1 and R2 are same. In that case, it will be equal to V1 plus V2 divided by 2. Okay, so this is one application. Okay, now consider another case where we have this circuit. I am measuring output voltage over here. Now I have this circuit diagram. This is grounded. Here I am providing a DC supply of 6 volt. Okay. Then this is my non-inverting terminal where I have two more supply voltages like this. Yeah. Okay. 2 volt, 2 volt. This is 10 kilo ohm. This is again 10 kilo ohm. And the feedback resistor is also having a value of 10 kilo ohm. Now what you will do when this case arises? This is my source resistance Rs and this having value of 22 kilo ohm, and I want to measure output voltage V0. Now here you need to calculate the value of Rs such that V0 will become 0. Okay, what you need to do is calculate the value of resistor Rs such that output voltage V0 becomes 0. Okay, so what you will do in order to find out the value of Rs? Okay, see, this is the home assignment for you. You just try to calculate the value of Rs. The hint is that you need to use superposition theorem. Okay, so what we will do using this superposition theorem, this 6 volt battery will be suppressed and hence the non-inverting terminal now become grounded. Okay, what we will do using the superposition theorem, we will suppress this 6 volt battery initially so that we will replace this 6 volt by ground. Now this will become inverting amplifier. Okay, inverting summer amplifier, and just find out the output voltage in that case, and let us call this output voltage be V01. Okay, so you need to find out V01, and then in the next step you need to suppress these two 2 volt batteries. Okay, so we should replace these 2 volt batteries by ground, and hence you will be able to find out another output voltage that is equal to V02. So output voltage V0 will be equal to V01 plus V02. Once you got this value of output voltage, this output voltage will include the equation of RS. Okay, so just find out the value of RS in this particular case. Okay, why? Because we have to find out the value of RS when output voltage V0 equal to 0. Okay, so in this equation you need to take V0 equal to 0 and calculate the output voltage RS. Okay, so just try to find out this value of RS. Okay, I will provide you with the solution in the next upcoming lectures. Okay, so we shall stop here. Okay, we have gone through three typical applications of operational amplifier. One is the voltage follower circuit, another one is the inverting summer, non-inverting summer, which is also known as adder circuits, and then we have seen the averager circuit. Okay, so we have seen that two voltages can be added to get the output voltage. Similarly, we may have two voltages which can be subtracted. Okay, and that circuit most probably should be known as subtractor circuit. Okay, so in the next upcoming lectures we will try to go through the subtractor circuits of the operational amplifier, and then we will move on to the integrator and differentiator circuits. Okay, how you can integrate the output voltage, or sorry, input voltage, and how you can differentiate the input signal voltage. Okay, that is what we are trying to cover in the next upcoming lectures of analog and digital electronics. Okay, so we shall stop here. If you have any questions, then you can ask.